Hello and welcome back to Statistics 1. We are starting chapter 3 on descriptive measures. And we are going to first talk about measures of the center. So there are three measures of the center which we are going to learn: mean, median, and mode. It's the perfect way to make it confusing, so get them all to start with the same letter, right? Mean, median, and mode. So let's talk about the mean. Mean, evil, right? No. Just kidding. So what is the mean? The mean of a data set is the sum of the observations divided by the number of observations. So that's what the mean is. So the mean is the sum of all observations divided by the number of those observations. I am going to write the formula in this most precise mathematical form and then explain what it means. The section decided to put the formula all the way at the back after the whole explanation. So if you have a mean, we are going to before I do that, observe that sample or population are not mentioned in the definition. See that? It says data set. Data set could be either population or a sample, right? They're both data sets. So we actually have the population mean, and then we have the sample mean. Yes?
Would this be the same as the frequency distribution, where we divide the frequency by the number of observations?
No, because you're dividing each individual one. Over here is the sum of all. So that's the difference, right? So this is the data set. So you have the other word for this is average. You are used to that one, right? You take your grades. Let's say all three exams are the same weight, because there is something called weighted average, which is what you have in this class. First exam 10%, next one is more, and the next one is more, right? So you can't just take a simple average. This is the simple average. You just add things and divide by how many there are. So I'm going to write the formula for this as x bar is equal to sigma, which is another Greek letter, sigma from I goes 1 to n of xi divided by n. Hey, look at that. Beautiful, right? Beautiful. Now, look at the screen. This over here is the mean. So that's going to be the answer. You'll get 7 or 1.9 something, right? So that's the answer. That's the mean. Now, n is the number, the size of your population or a sample. Let's say you have 4 algebra tests. So n is 4. Or you're going to average the age of 10 people. N is 10. if you need to write it next to it. The top simply means sum of all observations. This is the sum of all observations. This letter, Greek letter sigma, stands for sum. The little I is the counter. And we need to learn the sigma notation because this notation shows up here, shows up in many places in this course for standard deviation and so on. It's fairly simple. It's just a notation and, you know, it looks scary, but let's first decipher the notation and then we'll go and learn more of statistics. So, if I want to write 1 plus 2 plus 3 plus 4 plus 5, I can simply put that as the sum of I, where I goes from 1 to 5. So what happened here? I is going to take integer values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and goes forever to infinity. So I is going to take all of the integer values. Now, these two instructions here on bottom and the top say start counting at the value that the bottom has and end counting at the value that the top has. So those are the instructions. So the bottom, right? The bottom one says start counting at 1, in this case, and the top says end counting at 5, which is why we added 1 through 5. And now you can introduce formulas. You can say I squared minus 1. I starts, let's say, at 3 and ends at 6. So let's say this is the formula that you have to deal with. You won't, but let's say. It's just learning the notation. So the first number that I is going to take on is 3. So the first term is 3 squared minus 1. Plus, the next number it takes on is 4, so 4 squared minus 1. The next one is 5 squared minus 1. And the last one is 6 squared minus 1. Yeah, you can go and compute and get the value at the end. But the most important part is to get familiar with the notation, what that notation means. So this I is simply a counter. I don't want to call it a variable because it's not going to be 1.7 and 3/2 and stuff like that, right? It's just going to be integer values. So it's a counter that counts over natural numbers. You can start at 0, you can start at 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the top number here is going to limit how far you go with the counting. And the bottom number tells you where to start with the counting. So now, if I have a summation of x and the index I, where I starts at 1, and let's say ends with 4. Now observe that the one on the top ends with n, right? So our formula ends with n. We have this n floating around. We'll understand that. But when you are looking at the notation only, and you go xi, right? So what this means is x1 plus x2 plus x3 plus x4. These guys over here are individual observations. So if I am to average 4 algebra tests for every student in the classroom, you're going to have different values, different combinations of values for x1, x2, right? Because it's very rare. I mean, it's not that rare in algebra course to run into 3 or 4 students that are going to have all hundreds across, right? So it happens pretty much every class that I have for algebra, that I have at least 2 or 3 students that have all hundreds across the board, and then 90s on the final. But if I'm looking only at the 4 exams, right, a student might go and say, all right, 36, 54, 81, and 92, right? And then the next student, the ones that are not so much favorite, 98, 71, 33, and then 0. Right? So it's much better when it's the other way. So you have 4 observations, and observe that I'm not using particular exams. This just stands for exam 1, exam 2, exam 3, exam 4. And then, depending on student to student, these numbers are going to be different. So that's the reason why these numbers are variables. You see, over here, I don't have x. I just use counter. So it's concrete numbers, 1, 2, 3, 4, 5. Over here, I have x, which represents a variable, which could be age, it could be weight, it could be height, it could be score on a test. It could be whatever you want to average, right? The average amount of basketball hoops, right, and scores, right, that the team had for the entire season. There are seasons in basketball, right? Oh, good. So, I know there are seasons in a year, like summer and fall and summer and those seasons. Seasons in the sun. So, you simply pick the numbers and you plug in. So now, what is the meaning of the formula summation I 1 to n of xi divided by n? Well, this means, again, you have this big fat division over here, divided by n, that you can't change that. What means on top is the first number you are adding is x1, then x2, plus x3, plus x4, plus x5, plus dot, 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 going forever, xn minus 1, that's the one before the last one, and then finally the last one is xn. With having this n in a formula, we are allowing for any number of observations, right? If this was the formula for mean, then that would mean that you have to have only 4 observations. And you cannot find the mean if sample has 5 things, or if the population of this classroom is 30. I can't take the mean because the formula was defined to have only 4 entries. So this n over here allows for any number of observations. So if I am observing a sample of size 4, I want to add their ages and divide by 4, I can use that. But if there are 30 people, then I change this to 30. And then I use 30 of these x's to represent each individual one. So when you look at the formula and the definition of this, it says it's the sum of all of the data, and that's this part, sum of all of the data points, divided by the how many you have. Well, if you're adding 30 weights to find the weight, you divide by 30. If you're adding 4 in a sample size, then you're dividing by 4. So these 2 numbers have to match, which is the number of observations that you are adding divided by how many observations you have, which is the same number. So this formula looks intimidating, but I am 100% convinced that the entire classroom used this formula many times in your lifetime already. Because it's a simple average that you all know. Add all the values, divide by how many they are. And that's the end of the story. So you can calculate the average household income in a neighborhood. Take the sample in the neighborhood of 10 households, and there are those that start the entire household in, maybe 30s or 40s. going all the way to maybe 250,000 a year for a particular neighborhood. And you have, let's say, 6 of those. You will add all of those individual amounts on a pile and divide by 6 because your sample size was 6. And then you infer from there that the neighborhood, the average salary, right, for the entire neighborhood, which means population, looking at the sample, is going to have so-and-so income per household, right? Now you know well, very well, you know that one household is making 55 and another household is making 210, right, a year. And you know that average is not representative, which is the reason why I don't like the average score for exam 1. Like I give the Calculus 3 exam back last night, and before I gave the test back, a student says, "What's the class average?" Completely irrelevant. Because if the lowest grade in a class is 34, and the highest grade in the class is 107, and the average is 73, right? Those students, it's completely off, right? So average is, you know, in my opinion, in some cases, completely irrelevant. So when I return the exam, if you choose to have one, right? If you ask me what the average is, I can look it up. It's not a problem because the software where I plug the grades in returns the average automatically without me asking for it. But the key is that, as I said, if the average is 83 and there is a 34 in a class, that average means nothing for that particular individual. All right, so let's see the way we use this. So, say we have household income. This means if everyone is working in a house, kids might be working, might not be working, going to college, whatever. So the entire household put all the money on a pile. So household income mean. Now, I'll put in thousands because I'm not going to write 55,000, 100,000. I'm just going to write 55, 100, and so on, and you know that it's in thousands, so you will add those 3 zeros at the end of your calculation. So what is the, let's invent the data. Data. So you go to the neighborhood, do the random sampling. You learned the way to do that in chapter 1. And you come up with data. So went door to door, and here are the, so 68, 57, 103, 98, 63, 66, 89, 107. So this is your sample. To find the average, the formula becomes 1, 2, 3, 4, 5, 6, 7, 8. 1 to 8 divided by 8. There are 8 data points in a data set. And that n, which is the sample size or population size, becomes 8. And we are going to now use 8 in the formula. So now this means that the formula is x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7 x8, there we go. Everything divided by 8. So now what are these x1s and 2s? Well, those are the numbers that you have above. So 68 goes here, 57 goes here, 103 goes here, right? And each one of these numbers goes into the variable. So this gives us that the average, like the mean household income is, and now you're going to add all of these numbers. So we have 68 plus 57 plus 103 plus 98 plus 63 plus 66 plus 89 plus 107. It's a busy work, right? Divided by 8. Wait for some wonderful, wonderful, wonderful data sets for homework. Yes? Problem says use 2 decimal, 3 decimal. They say 100 or a tenth or something. So in our case, 1 decimal is fine for this example. If you're dealing with money, 2 decimals for cents. That should be common sense, right? You also follow the numbers that are given to you. Generally, you can't invent precision. If your data is given in 1 precision, you can't be more precise than that. So I would say for this, if you really want decimals, 1 decimal max, because all of the numbers that you have are whole numbers. So there is no reason to give me a 7 decimal precision here because, right, it's whole numbers. What is the answer over here? I'm sorry? 81.4. Are we all 81.4 on this? With a smile? Come on. Where are the smiles? It's math. Should be happy. Imagine the alternative, guys. Not doing this. Life would be miserable. Miserable. So just smile, all right? So what is the mean household income? The mean household income is 81,400. That is the, so you can write the sentence. Oh, by the way, I told you that every problem in statistics is a word problem, which means that every problem must have a sentence answer at the end, saying this is what is the conclusion of the problem. So right now we have to write a sentence to this word problem, which says mean household income is $81,400. You can write whatever sentence with all the details, right? Well, obviously, the better sentence you write, your thing will be chosen over those who don't. Yes? What happened?
You still want, like, you know how you put, like the mean equals 81.4, you still want to, like, box.
Do I want it boxed? If it's boxed, I'll take it boxed. If it's not boxed, I'll take it non-boxed. What I care about is this one over here, because this is where your 2 points are for the correct answer. All right? This line over here, guys, you see the big fat arrow pointing? You see this arrow? This is partial credit. Yeah. If this problem was 10 points on the test, this sentence over here is 2 or 3 points. That leaves 8, right? This line, whether it's boxed or not, right here, is like 1 or 2 points worth. So up to this point, you have 8 points, and then 2 for the sentence is 10 for the whole problem. So what are you supposed to, if you were going to box anything, you box the sentence, because that's the answer to the question. But you can leave the sentence there and box this, that's fine, I won't. You know.
For the actual work, that x bar equals 68 plus 57 plus 103, we can just show that.
Yes.
Just that.
Yeah.
Everything above.
So data will be there. So what are the things that you need to write? I mean, first of all, this is not algebra, so you're not graded step by step, right? We are agreeing right now that sentence answers, questions, and the word problems and all of those require sentence and answers back. Now, it's math course, so there's going to be calculation in between. So when you ask me a full sentence question, which is not starting with yo, I will give you a full sentence answer that is not starting with yo. All right? If you start your full sentence question with yo, I will ignore your email. So that's very simple, right? 100% of workforce, no matter where you are, is word problems. You sit in a meeting, there are words. No one shovels equations in a meeting. Even scientists don't shovel equations in a meeting. They talk, right? So there is a question which is asking you, what is the mean household income for this neighborhood? Here's the data. Blech. You go do some calculation on a napkin or a paper or directly on a calculator or a surface on a desk, or you take a paint and just do it on a wall. No one cares. What people care about is you providing the sentence answer back. So in a meeting, you were tasked with you're working now, right? Making those tens of thousands or hundreds of thousands. And in a meeting, your job, your assignment is to figure out what is the mean household income for such neighborhood so something can be done. You go to your cubicle or office or home or whatever, you do these calculations and no one cares what you did, and you're coming back with the answer in an email or a written report or whatever, which says the mean household income is. The world cares about the question and the sentence answer. This thing in between? Yeah, we grade you in class and so on, but no one will ever care to see anything. Now, how you make me happy in terms of the exam, if you mess up to have your partial credit, because we know how important the 70% of the bridge is. Formula, spelled out problem, answer, and this. So 1, 2, 3, 4. This stuff, well, this is given to you. This stuff you don't have to have over here at all, right? But this way, I know that you know what you're supposed to do. You skip this step. It's still full credit if this is correct, right? If you don't write the formula, it's still full credit if this is correct. But you have to understand that if you go from the question, you punch everything in a calculator, you mess something up, you get 89 over here, and there's nothing in here. I have no clue that you're familiar with the concept, and what kind of a partial credit are we talking about? So it's a 0, exactly. So you want to cover yourself, right? And write these things so that if this is 89, I say minus 2, so you can go and facepalm yourself, right? So you get 8 out of 10. If you have a wrong answer, because I know you know the formula, you know exactly what you're supposed to do, the way it works, and now you can't operate the calculator, so, you know, go home and facepalm. There's nothing I can do, right? Or get your finger to be thinner, I don't know. Whatever it is. That's your problem. So, right, in terms of grading, it's very simple. If you show all of the work, there will be maximum amount of partial credit if this is not right. If there is nothing and this is wrong, it has to be 0 because 0 work, right? And 0 compensation for the 0 work. I hope that all makes sense. And that's the mean. We are done with the mean. It is time to talk about the next one, which is the median. So the median. All right. So the median divides, actually the median is the number, no, the observation, sorry. The median is the observation which divides the bottom 50% of the data set from the top 50% of the data set. This definition is not in the book. It's abbreviated in a paragraph, but they do give you a definition which is actually a procedure. So they kind of mess it up a little bit, but this is not a big deal. So median is the observation. It's a number which divides 50%, bottom 50% from top 50%. Now, this clearly, if you think about it just for a second, clearly entails that you have to put your data in increasing order. You have to order your data. See this data that I have on households? Clearly, I have 8 observations, so it's going to be 4 and a 4, right? So median is, but if I draw the line here, that's not median, because look, this one has 103, this one has 107, right? So how's 103 in a bottom 50%? It makes no sense. You have to think about these things when you start learning and reading these, right? If there is a bottom 50%, then you better have the smallest number in the 50%, bottom 50%, and the highest numbers in the top 50%. So just slashing the data in half doesn't work. So step number 1 for median is to put the data in the increasing order. So arrange the data in increasing order. Step 1. Arrange data in increasing order. Then, step 2 is breaking into 2 parts. If n is odd, median is the middle number. If n is even, median is the average of 2 mid numbers. So let's go back to our households. Can anyone read me the numbers so I don't have to go back and forth? So let me just see. Households So we have 68,
57,
57,
103,
103,
98,
98,
63,
63,
66,
66,
89,
89,
107.
107. Thank you. So this is my set. I have 8 data points here, 8 observations. So this falls into n being even. For this data set, n equals 8, so it's even. Step 1 is to arrange data in increasing order, meaning smallest number first, that's 63. You can cross them. That's what I said, please pay attention, I was just testing you. So 57, no, very good, very good. I mean, yeah, this is important. 63, 66, 68. 89, 98, 103, 107. No bingo, huh? No bingo. Okay, fine. No bingo. See you next week. So now we have the median is going to be a number that has 50% of the data on the bottom and 50 on the top. Now, that's clearly me putting the line right there. The problem is that that line is not on a number. It doesn't fall on a number. So what is the median? Median will be 68 plus 89 divided by 2. Because it's even. You have to average it. Because it's even. So that's 157 over 2, which is 78.5. So that's what the median is. So median 78.5. Another example. I'm afraid to actually go into the homework, because if I go into the homework, I'm probably going to find all of these wonderful data sets that oh no. Well, it's not that bad. Okay. Trying to find. I found the problem, but maybe I can do better. Alright, fine, we'll go with the. So, in the Winter Olympics, so we are 322 over here. In one Winter Olympics, Michelle Kwan competed in the short program ladies singles event. From 9 judges, she received scores ranging from 1 poor to 6 perfect. The following table provides the scores that judges gave on her technical merit found in the article, blah, blah, blah. Okay, so here's the data. Now, this is clearly population data because these were all of the judges. They had 9 judges, and they all gave their numbers. So 5.8. 5.7, 5.9, 5.7, 5.5, 5.7, 5.7, 5.7, 3 times, and then 5, 6 at the end. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 observations. What's the median? Well, we have to order the data from lowest number to the highest number. So 5, 5 is the lowest. Then we have 5, 6. And then we have 5, 5, 7s. And then we have 5, 8 and 5, 9. The good practice is once you order your data to count to see if you actually have the same amount of data points. So data has 9, and when you reorder the data, must have 9. Now, since you have 9, that means that you guys have the middle number, and that's 5.7, because you have 4 on the left and 4 on the right. So there is a middle number because it's odd. So n is equal 9, which is odd. And the median is 5.7, which is the observation. So you have both examples now. The example that we made up with the household income had 8 observations, and the median is actually not the part of the data set because we had to average 4th and 5th position to get the median. When the number of data observations is odd, then whatever is the middle observation is the median. The last measurement that we are talking about in this section is mode. So mode of the data set. Is the value which occurs most frequently. So, to elaborate a little bit more, if no value occurs more than once, then the data set has no mode. Otherwise, any value that occurs with the greatest frequency is a mode. You can have few different modes. So otherwise, any value that occurs with the greatest frequency is a mode of the data set. Please note it says a mode, not the mode. A mode. So you can have multiple modes for a data set. Well, first of all, let's go back to our previous example with the data set from 322. Mode is 5.7. This is the most frequent grade given. It was given 5 times. 5.7. All other grades were given only once. So mode is 5.7. And the median was 5.7. Now the average of the grades might not be 5.7. And we'll talk about the differences of these. Right. So that was that. Let's take a look at another set of data. So let's make up data. So this is another example, making up data. So let's say you have, and I'll put this data in the increasing order. So 13, 14, 15, 15, 15, 16, 19, 19, 20, 20, 20, and 30. So, what is the mode? Well, mode is the observation that occurs most frequently. All right, so 13 shows up only once, 14 shows up only once, 15 shows up 3 times. Oh, so does 20. Great. This is what we call bimodal, guys. Bimodal. Remember the bimodal one that looked like that? This is where the 15s are, and this is where the 20s are. Now, actually, what you are going to, let's do the dot plot for this. So if you do the dot plot, you will see the shape, and it clearly gives you that it's a bimodal. So let's go with the 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Could put 30. 30. There we go. Now, 13 only once, 14 once, 15 3 times, 16 once, nothing 17, 19 8, 19 twice, 20 3 times, and 30 once. You can clearly see 2 peaks on this one. It's bimodal, right? So the dot plot shows that distribution. So we have 2 modes here, 1 and 15, 1 and 20, because now if there was 1 less 15 or 1 less 20, then the mode would be the other number, right? So if you lose one of the 15s from the data set, then you only have 1 mode, which is 20, and that's it. Are we clear on this? Great. What's the median here for this problem? So, okay, it's even. So we have to find the middle and average. 1, 2, 3, 4, 5, 6. 16 and 19, very good. So 16 plus 19 divided by 2, which is 35, divided by 2, which is 17.5. 17.5 is not in our data set at all, but it's a median. How about mean? What do we do for mean? Add them all together, divide by 12. Good. So 13 plus 14 plus 15 plus 15 plus 15 plus 16 plus 19 plus 19 plus 20 plus 20 plus 20 plus 30 divided by 12. Nice. All right, what is this? 27 plus 45 plus 30, 48, 54 plus 90 So this is 99, so 189, and the 27, 216 divided by 12. Cancel by 2, it's 108 divided by 6, cancel by 2, 54 divided by 3, divide by 3, goes 1, 8, 18. Is it 18? All right, good. So now let's list them all. Mode, 15 and 20. Mean, 18. Median, 17.5. As you can see, for a given data set, these measures of the center do not have to align to be the same number. Sometimes they are, but most of the time they're not.
The example that you gave for the bimodal was just to show us you're not looking for that unless you ask the question.
Yeah, unless it said, yeah, but it could be included in the same question, represent the data with the dot plot. So it is exam question as much as find the mean or anything else. That was in chapter 2, the dot plot visual representation, and now in chapter 3 we are moving on with other things. But the most important part is us seeing the mode. So the peaks that we are getting, right? You have 2 peaks, so it's bimodal. And we see bimodal, 2 peaks. If your data set ends up something like this, right? This is not bimodal, right? You draw like this. What is this? Yes. So only one mode, which would be this observation here, whatever this number is. Let's say it's 12, and it's going to be skewed right.
Unimodal.
Yes. Unimodal. Very good. All right. Cool. You got it. Nice. So population mean, x average is equal to sum of all xi divided by capital N for population. Sample mean, x bar equals to summation of all xi's divided by lowercase n for a sample. So we just, mathematically distinguish. The formula, mechanics, everything is the same. And I already told you in which respect you guys could be population or sample, and it's the same people. So now we can just say n, population size, and n, sample size. And meaning size, we are meaning number of observations. So if you want to average the weight of 5 individuals, then the number of observations is 5. Now those 5 individuals might be a family of 5. That's the population, right? Or it could be 5 people from this classroom randomly selected. You give your weight, add, divide by 5, and we're done. Yes?
Going back to the formula, what does the XI? Yeah.
Now, each individual observation. That's the That's the talk we had for 15 minutes over here. So I excise each individual observation, and we go from I to n because one example might have 5, the other example will have 7, and so on. So we keep that as n. So you will stop at that value. So if you have, we did number of households, it had 8, but then we did whatever was the next thing, and it had 9. What was the next thing we did with the decimals? Oh, the scores for the Olympic thing. Other questions, concerns? No? Done. Yes. And we just stop.